body radiation means also you know definition. So how you will create the black body? You will take the hollow sphere, just hollow sphere. Okay, within the hollow sphere, we will make a small pointed hole, spin pointed hole. Using this one, we will send some light here. Okay, this light will multiple times reflect within the cavity and it will absorb. This is observing. So, and also after that, when you incident some light here, this is observing. Okay, once you heat this black body, suppose you are taking a some same black body. Okay, you are heating. Okay, you are giving some heat to this black body. Okay, you are giving heating. Okay, once you heat, so how you created black body? Here we have coated some carbon black or some metallic material, some material. Okay, some different kind of material. Okay, so once you heat this material, please mute. Okay, once you heat this material, what happens? Here also material means there is a huge number of atoms are there. Okay, how many number of atoms exist for a atom for a material? Suppose if you take any material, suppose how many atoms will be there? Anyone? So 501, are you there? 501.
Yes, sir.
So how many? What is the Avogadro number? You don't know Avogadro number? Okay, no problem. Okay, for a, if you take a for a particular volume, if you take particular volume, there is a 10 power 26 order of 10 power 26 atoms per a unit volume. Okay, unit volume. If you take a small unit of volume, there will be 10 power 26 atoms will be exist. Okay, that is the number of atoms in a per a volume. Okay, suppose here we quoted some material here. There is also lot of atoms are there. So if you heat this one, if you heat the black body, atoms will vibrate. They will get the thermal energy. Because of this thermal energy, they will vibrate. Okay, once they vibrate atoms, okay, they lost the energy or they emit the energy or they lost the energy in the form of radiation or in the form of waves, whatever you can say. Or you can say that atoms will vibrate because of the temperature heating or because of the thermal energy, and once they vibrate they lost the energy or they emit the energy. Okay, once they emit energy, and this will emit as they will emit the throughout the spectrum. Okay, all atoms will emit the energy. That is what whatever once you heat the black body, radiation will emit. That is what we are saying, black body radiation, emitting black body emitted radiation. Okay, you keep the here meter, some meter here, you can estimate how much radiation is emitting from the black body if you heat. Okay, if you heat the black body, how much radiation is coming from the black body, you can estimate using some meter. Okay, estimating, you can estimate. That is the black body radiation. This is emitting. Okay, this is emitting. So this emitting also, this can emit throughout the spectrum of the wavelength or energy or frequency, whatever you can say. Okay, so because of this one, it is absorbing complete light, and also once you heat this black body, it is emitting complete radiation. That means this black body is a perfect absorber and perfect emitter. Okay, absorber and also emitter. Okay, that is the main advantage of this, main characteristic feature of black body. Okay, it will absorb complete radiation and also it will emit. So depends on how much you are heating the black body. Okay, now if you plot the graph, whatever emitted radiation, so whatever emitted radiation versus, suppose this is the frequency we are taking, or you can take wavelength also, it's not a problem. Frequency or wavelength, just it is nu is equal c by lambda, right? So you can convert in terms of nu and lambda, whatever you want. Okay, this is the emitted radiation, or you can say emitted radiation. Okay, emitted radiation from what? Black body, right? So if you plot this one, okay, like it will get the spectrum like this. Okay, suppose this is a 2000 Kelvin, 2000 Kelvin. If you increase this temperature, what happens? This curve or this peak will shift towards the lower frequency or lower wave. You can take wavelength also, or whatever you can take. Okay, this will shift to the suppose I will take wavelength. It is convenient to easy to. Let's take wavelength. Okay, instead of frequency, this is easy to understand. Okay, micrometer or or you can take nanometer, or you can take whatever. Okay, so this curve is shifting to lower wavelength side. Okay, this curve is shifting lower wavelength side. Okay, this is suppose 3000 Kelvin, 3000 Kelvin. If you increase the temperature, the curve again will shift towards the lower wave number side. Okay, so here this is the maximum. Okay, this is the suppose you are giving the 2000 Kelvin temperature to black body. Okay, here you are giving, suppose how we are plotting this graph. First we are giving 2000 Kelvin to this black body. If you give this much temperature, this much heat, so some radiation will emit from this black body. Okay, that is we are plotting on the y-axis. Okay, we are plotting on the y-axis. So this is the curve we got. So again after that we increase this one like 3000 Kelvin. Okay, 3000 Kelvin, and if you increase the temperature, what happens? The emitted radiation also increases, right? Isn't it? Emitted radiation also increases, so this intensity also increasing. Emitted radiation is increasing means this intensity peak height also increases. If you increase after that, if you suppose this curve is like 5000 Kelvin. Okay, if you increase further temperature, this curve also increasing. Okay, this is the here maxima, and suppose here this is the I'm drawing this one. Okay, here this is the maxima, and here this is the maxima. So maxima is shifting. How it is shifting? How it is shifting this maxima? How it is shifting to lower wavelength side, right? Isn't it? Do you observe this one? Hello?
Yes, sir.
So if you heat the black body, if you increasing the heating means you are increasing the temperature. Okay, if you increase the temperature, this curve is shifting. This is lower wavelength side. Okay, this is the wavelength, this side is increasing, right? Suppose this is 500 micrometer, this is 1000 micrometer. Okay, 1000 micrometer, and this is 2000 micrometer, like that. Okay, so how it is, this is maybe 200 micrometer. 200 micrometer. So how it is decreasing? If you increase the temperature, the curve is shifting lower wavelength side, isn't it? You can clearly see the in the diagram. Okay, how it is shifting. So if you heat the temperature, your intensity of the emitted radiation is increasing. So here you have a black body. Here you have a black body. You are increasing the temperature, but here emitted intensity radiation also increasing. Why it is increasing radiation? Why it is increasing radiation? If you increase the temperature to the black body, why the radiation of the black body is increasing? Please anyone answer this one. So we are increasing the temperature to the black body, but after increasing the temperature, the emitted radiation from the black body is increasing. Why it is increasing?
Because electrons emits
Yes, yes. Okay, that's good. Okay, why it is increasing means here already we have discussed, we made one point here. There is a number of atoms in a.
Sir, when it
uh,
gets heated, it gets excited to another level, no, sir. So it will emit radiation.
yes, yes, good, good. Okay, so here already we have discussed. Okay, here we have quoted some material. There is a atom. If you increase the temperature, they are getting more energy. These atoms getting more energy. They are vibrating more. Okay, vibrating more, vibration also more, and they are losing energy more, or they are emitting more energy. If emitting more energy means radiation intensity also increases, right? Intensity also increases. That's why if you increase the temperature, the intensity curve also increasing. So one more question here. Why up to here see the plot in the plot. So up to particular suppose up to particular wavelength it is increased, right? So suppose take first curve, this is first and second and third curve. Okay, so here point is, so if you here we are fixed the temperature 2000 Kelvin. Okay, 2000 Kelvin. So up to particular temperature, up to particular wavelength is increased. After that slowly decreased. Why it is decreasing? Why this trend is following? Okay, up to particular wavelength, the intensity is increased, right? Emitted radiation intensity is increased. After that, this emitted radiation is decreasing. How it is decreasing? Why it is decreasing? Please answer anyone. 5. Yes.
Because excited state is unstable, no sir.
Hmm.
So after some time it will come to its stable place.
Yes. Okay. And okay. What's your name? 35. 535.
Vishwanath sir.
Vishwanath. Okay. So that is also one kind of answer. Okay, good. That is also answer. Okay, see some, we will see some example here. So here we will see. Suppose you are you have a one gas or some wooden what we will say wooden poi మన ఇంట్లో పొయ్యి అంటాం కదా. So you are burning some sticks here. Okay, you are burning some sticks here. Okay, while these sticks are burning, you will get the maximum temperature, right? This will maximum temperature will be emitted. Suppose you are boiling water or something else. Okay, you are boiling some water, maximum temperature will emit from this, or you can any solid material, anything you are heating. Okay, you are heating. So up to you are using some sticks and you are using heating this element. Okay, so up to particular temperature this will heat up. Okay, once these sticks are completed, okay, sticks are completed. So the otherwise you can say here, see here we have discussed here atoms are already you have given some temperature. Okay, you have given some temperature. There almost all atoms are excited. All atoms are excited and they emit the maximum energy. Okay, maximum energy. So here there is a suppose there is a number of atoms here. They are going up and down, excited state and coming down also. So there is a generally if you take any atom, there is a many energy levels, right? Many energy levels. Suppose if you give some temperature, suppose T1 temperature, suppose here atoms, some atoms will go to the excited state. If you increase further temperature, here deep level atoms also go to the excited state. Okay, like that, all if you increasing the temperature, okay, more number of atoms go to the excited state, and also most of the atoms will excite or most of the atoms will vibrate. Okay, most of the atoms will vibrate, and after that there is no atoms to vibrate. Okay, that's why at particular temperature we are getting the maximum peak. After that slowly this radiation also decreasing. Okay, this radiation also intensity also decreasing. Like that similarly, if you increasing the temperature, this peak intensity increasing for different temperature, this intensity also different. Particular temperature where why we are getting here maximum peak means maximum number of atoms vibrated up to that temperature. Okay, after that the intensity is slowly reducing because almost all atoms are excited or all atoms are emit the radiation. There is no atoms to emit further radiation. Okay, that is why we are getting the maximum intensity at particular wavelength. After that, if you increasing, why this shift is why the maximum of this peak is shifting lower wavelength side? Anyone? So here see, first case, this is the maximum, right? Peak maximum. Second one, this is the maximum. Third one, this is the maximum. Why this is shifting? We are observing lower wavelength side. Anyone?
Higher temperature.
Ah, yes. What happened? Yeah. Try just think of it.
After some time, it loses its energy and comes back to ground state, no sir.
Ah, yes. That's why we are. If after some time this peak is decreasing, that is okay. But we are the maxima. Suppose we are varying the temperature. Okay, we are changing the temperature. This peak is shifting lower wavelength side. Okay, here the suppose if you draw one line here, this is suppose 500 micrometer. Here maybe 490. Okay, here maybe 400. Okay, right? This is the 400. This is the 490. This is the 500. So what happen if you increasing the temperature, the peak maxima, this is lambda m, is shifting lower wavelength side. Why it is decreasing? You know this is answer. You know.
Up
So
to certain temperature, it increases, sir. When it reaches the limit and then it decreases.
it's not like that. Okay, see here we'll see the this one. Okay, if you eat the temperature, what happens? Radiation also increasing, right? The radiation also increasing from the black body, right? Isn't it? The radiation also increasing, right? Right?
Yes. Yes, sir.
radiation is increasing, radiation intensity or energy is increasing. That means energy also increasing, right? Radiation increasing means nothing but energy, emitted energy, radiation energy is increasing, right? Isn't it? So
Yes, sir.
if energy is increasing means what? E is equal to what? Hc by lambda, right? Hc by lambda. So here E is inversely proportional to the lambda. Lambda means what here? Wave
Wavelength.
length. So if increase the temperature, energy is increasing. Okay, energy is increasing. So if energy is increasing, the lambda will decrease, right? So here what is happening? The lambda is decreasing. In this curve, we are increasing the temperature. 2000 Kelvin, 3000 Kelvin, 5000 Kelvin. We are increasing the temperature, but this lambda is, this curve is shifting lower wavelength side. That means intensity, radiation is increasing, so the wavelength is decreasing. This is the simple relation. This is, you know, but you could not correlate this one. Okay, that is the reason for this type of curve and why this curve is shifting lower wavelength side. Okay, this is the simple black body radiation. Okay, it is a, once you incident the light here. Okay, once you incident light here, this will completely multiple times reflect within the cavity, and the light will absorb. Once the all light of the spectrum will absorb, it will looks like a dark. Okay, that is the complete absorption. Okay, that means black body is a perfect absorber. Okay, once you heat the black body, once we heat the black body, the atoms will get the thermal agitation and they lost the energy or they emit the energy, and this energy also it covers the throughout the spectrum, EM spectrum, electromagnetic spectrum. Okay, that is UV to IR region, UV ultraviolet region, and visible region and infrared region. Okay, that is the, once you heat the temperature, if you increase the temperature, more radiation will emit from the black body. That is the, so from this absorption and emission, this black body is a perfect absorber as well as perfect emitter. Okay, that is the things. Okay, after we plot the emitted radiation as a function of wavelength. So first, if you increase the temperature, the maximum of the curve, wavelength of the curve will shift to lower wavelength side. Maximum of the curve will shift to lower wavelength side, and also if you increase the temperature, intensity of the emitted radiation also increases. That is the 2 points you can conclude from this graph. Okay, that is the black body radiation. Now using this black body to explain this black body, there are different people proposed few relations. Okay, we will see that relations. First one, okay, these are black body radiation loss, or you can say black body radiation loss, or you can write whatever you can write. Black body radiation loss. Okay, first one, Stephen Boltzmann law. Okay, Stephen Boltzmann. So most of the try to explain this black body. Next one, Wien's law. Okay, Wien's law, and third one is Rayleigh gene. Okay, Rayleigh genes law. Okay, Rayleigh genes law. Okay, Rayleigh genes law. And fourth one, Planck's law. Okay, Planck's, already we'll discuss this one also. Planck's law. This is the, we have syllabus. This is, we don't have syllabus, but you should know what is this last means. Okay, so these people tried to explain the black body radiation. Okay, these are the what we have present laws. Okay, first one, Stephen Boltzmann law. Whatever, first one. Okay, first one, whatever emitted radiation from black body is proportional to the fourth power of the temperature. Okay, this is the first law. Okay, what is this one? E means whatever emitted radiation from the black body, emitted radiation from the black body is proportional to the fourth power of the temperature, T to the power of 4. Sigma is the some Boltzmann constant. This is the Stephen Boltzmann constant. Okay, this is some constant. Okay, the derivation no need for this laws, only Planck's law only we require derivation. Okay, this is, there is no derivation, just we will write direct formulas. Okay, is proportional to the T power 4. Okay, that is the first relation. Second one, Wien's displacement law, whatever emitted radiation in terms of frequency, you can write 8 pi, just a second, I will write this direct expression, 8 pi 8 pi h nu cube by h nu cube by c cube into 1 by e to the 4 of h nu by kt. Okay, this is the Planck's Wien's radiation law. Wien's radiation law. This is Wien's radiation law. One more law is here. Suppose 2IR 2A. Let's take Wien's displacement law. Wien's displacement law. Okay, he proposed two things. Displacement law. Please note down these laws. Okay, here lambda m into t is equal some constant. Suppose this is the some constant. This is constant, some constant. Okay, just before we have discussed, right? Here lambda m inversely proportional to the temperature. Okay, lambda m inversely proportional to the temperature. Just now we have discussed, right? Why lambda m is shifting lower wavelength side if you increase the temperature, isn't it?
Yes, sir.
Yes, this is the
Yes, sir.
Wien's displacement law. Lambda m means maximum of the curve. Okay, maximum of the curve is shifting lower wavelength side if you increase the temperature. That means lambda m is inversely proportional to the temperature. Okay, and third one is Rayleigh-Jean's law. Okay, we will see this one also. Rayleigh-Jean's law is E of nu. Nu means here frequency. Okay, don't confuse. Okay, 8 pi nu square by c cube. This is c cube. Okay, c cube is into kt, some kt. Okay, these are first is the Stephen Boltzmann law. That is whatever emitted radiation from the black body, is proportional to the, or you can write equal to sigma into t power 4. That is, t is the temperature of the black body, is the emitted radiation from the black body. Okay, second one is Wien's law. This is Wien's law is E of nu, emitted radiation from the black body as a function of frequency is equal to 8 pi h nu cube by c cube into 1 by e to the power of h nu by kt. Okay, this is why we have written here this emitted radiation is depending on frequency or wavelength. Okay, that's why we have written. So this law only explain okay, I will explain. Okay, third one is Wien's displacement law. That is lambda m into t is equal to some constant value. That is lambda m is proportional to the inversely proportional to the temperature. That means just before we have discussed. Okay, curve is shifting left and side, lower wavelength side. This is the lambda maximum lambda. Okay, this is shifting towards lower wavelength side. Okay, that is the this Wien's displacement law explains. Okay, third one is this is Rayleigh-Jean's law. Rayleigh and Jeans, these are both two scientists proposed this law. Okay, E of emitted radiation from the black body is equal to 8 pi nu square by c cube into kt. Okay, kt is the some thermal energy, nu is the frequency of that atoms. Okay, so this energy here, see, in this expression, this E of nu is proportional to nu cube and also proportional to 1 by e to the power of h nu by kt, right? E to the power of h nu by kt. It depends on two terms, frequency. Okay, here in this expression, E of nu is proportional to nu square. E of nu is proportional to nu square. Okay, so this law, Rayleigh-Jean's law, only explain IR region. IR region. Okay, this is explain IR region. Okay, and this one explain this Wien's law is explained only correctly explained in the UV region only. Okay, that they could not explain complete spectrum. What is our spectrum? UV visible IR, right? Okay, UV visible IR, but they are explained half of the portion only. They could not explain complete spectrum. Why they could not explain complete spectrum? Because they have used some of the classical mechanics formulas. So that's why they could not able to explain complete formula. Okay, complete spectrum. So here, see, here how we got the spectrum. Suppose here too, like this, right? We have this is the emitted radiation from the black body, and this is the frequency or wavelength, whatever you can take. Okay, we have got the this much spectrum. So here, if you take wavelength, suppose if you take wavelength, this is UV region, and in the middle visible region, and at the end IR region. Okay, this Rayleigh Rayleigh jeans and Wien's law, they could not explain complete spectrum. Some law explained up to UV region only. Other law explained only IR region only. They could not explain complete spectrum or they could not explain visible region. Why they could not explain? Because they have used some classical mechanics formulas, so they could not, or they used some classical mechanics laws, so they could not explain. So after that, to sort out this problem, so Planck's proposed one more laws. Okay, Planck's radiation laws. Fourth one is very important. This one, Planck's radiation law. Planck's law radiation law, whatever you can write. This is not a problem. Okay, Planck's radiation law. Okay, this is very important. Okay, we will discuss this one. Okay, please note down this one. Are you noting down this one? Are you following running notes?
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, while giving notes, maybe we will not cover these all points. Okay, maybe whatever important we will cover in the notes. So if you follow running notes, that is very easy. And right now you don't have any exams, right? You don't have any exams, so you have plenty of time. So you have enough time. So just you try to understand the subject. Okay, don't no need to by heart formulas and these things. Just try to understand subject and you follow the running notes and you write down some notes. Once you get time, free time, maybe 5 minutes, 10 minutes, just go through the notes, then you will understand. Or you can google it, wherever you have problem, google it, or you can message me. Okay, you can understand the complete problem. Just you try to learn the subject now. Just no need to by heart the concepts. Okay, that is why. Okay, we'll that way we'll discuss the problems or concepts. Okay, this is the two, three laws. So these four people also tried to explain the black body radiation, how the, if you give the temperature, if you change the frequency, how the radiation is emitting, how it is depending on frequency and wavelength. Okay, they proposed some laws. They derived some expressions for the black body radiation. That is what we have discussed, three expressions. Now we'll go to the Planck's radiation law. Okay, why we need this Planck radiation law came up, this came into picture. First, Stephen Boltzmann law explained only uh, in the uh, function of temperature only, that is whatever emitted radiation is equal to the temperature to the power of fourth power of the temperature. Okay, and second one, Wien's law explained only UV region only, but we have spectrum of UV visible IR region, right? We have broad spectrum, but it could not explain complete black body radiation spectrum. Okay, whatever radiation is emitting from the black body, it is covering complete electromagnetic spectrum. That is, what is the range of spectrum? Electromagnetic spectrum, UV visible IR, right? So they could not explain the remaining portion of the spectrum. Okay, after that, this Rayleigh and Jeans came up and they also derived some expression. They are also explained only IR region. They could not explain UV region and they could not explain visible region. Okay, they are also failed to explain complete spectrum. To overcome these drawbacks, to overcome these failures, Planck came and he proposed some laws and he proposed some statements. Okay, after that he derived the expression for black body radiation. He could explain the complete spectrum, that is UV to IR range. That is we are going to solve now. Okay, we are going to solve Planck's radiation law. Okay, just a second. We will take new page. Okay, up to now, any doubt? Are you having any doubt?